We'll start in 1 minute. Today we'll be in section 8.3 again. The second half is on moments and center of mass. Center of mass is also known as center of gravity. So we start with a quote from a famous Greek mathematician, Archimedes. "Give me a place to stand and a lever long enough, and I will move the earth." So here's the law of the lever. Suppose two particles with masses m1 and m2 are attached to a rod or on opposite sides of a fulcrum at distances d1 and d2 respectively. The rod will balance if the mass m1 times the distance d1 is equal to the mass m2 times the distance d2, with the center of mass being at the fulcrum. So the rod of insignificant mass, so we'll suppose the mass of this one on the left is m1 and the mass of the one on the right is m2. Suppose the balancing point or the fulcrum is right here, and the distance from particle m1 to the fulcrum is d1, and the distance from the fulcrum to the other mass m2 is d2. And if it's balancing, then the product m1 times d1 is equal to the product m2 times d2. And at the fulcrum is the center of mass. Okay, on the x-axis, let x1 and x2 be the locations of two particles with masses m1 and m2 respectively. And let x bar be the location of the center of mass. So we'll draw another diagram. We have the x-axis. We have a point x1 and a point x2. And at each of those points, we have a particle. This particle has mass m1. And this particle has mass m2. And the center of mass is x bar. So this is where the fulcrum would be. Okay, so notice the distance. This is the regular oriented x-axis, positive numbers to the right, negative numbers all the way to the left. So the distance from the point x1 to x bar, the larger number x bar minus the smaller number x1, that's the distance. And then the distance from x bar to x2, the larger number x2 minus the smaller number x bar. Okay, so the law of the lever says that if we multiply the mass m1 by the distance x bar minus x1, that's the distance to the center of mass, that's equal to m2 times x2 minus x bar. Okay, so the goal here is to express the center of mass x bar in terms of x1, x2, m1, and m2. So in other words, solve this equation for x bar. Okay, we distribute multiplication over subtraction on each side. So on the left-hand side, we get m1 times x bar minus m1 times x1. On the right-hand side, m2 times x2 minus m2 times x bar. We want to solve for x bar, so every term that has x bar in it, we want on one side of the equation, and every term that doesn't have x bar on the opposite side. So we can get that in the next step. We'll do two things at once. We'll add m2 times x bar to both sides, and we will also add m1 times x1 to both sides. Okay, when we do that, we get m1 times x bar plus m2 times x bar. And on the right-hand side, we get m1 times x1 plus m2 times x2. Okay, then on the right-hand, or on the left-hand side, we factor out the x bar, so we get m1 plus m2 times x bar equals m1 times x1 plus m2 times x2. And then divide both sides by the quantity m1 plus m2. We get x bar equals m1 times x1 plus m2 times x2, all divided by m1 plus m2. Okay, but remember what x bar is. X bar is the center of mass of those two particles positioned at x1 and x2. Okay, so that's the formula for the center of mass if you have particles on the x-axis, or center of gravity, if you want to call it that. Hey, a term, moment. The moments of the masses m1 and m2, one of the moments is m1 times x1, and the other moment is m2 times x2. So you could summarize this center of mass. In the numerator, we have the sum of the moments. Add up the moments, sum of the moments. And in the denominator, we have the sum of the masses. Okay, we'll generalize this. On this one, we just had two particles on the x-axis. So on the next page, we'll generalize that concept. So in general, if n particles with masses m1, m2, and so on up through m sub n are located at points x1, x2, and so on up through xn on the x-axis, then the center of mass is located at the sum of the moments divided by the sum of the masses. So the moments are m1 times x1 plus m2 times x2 and so on. And the last moment that we add is m sub n times x sub n. And then we divide that by the sum of the masses, m1 plus m2 plus dot 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 plus m sub n. You can use sigma notation in the numerator. We add from I equals 1 to n, and the individual terms have the form m sub I times x sub I. And in the denominator, we're adding the masses, so we can write sigma I equals 1 to n m sub I. So I sort of used some space that I wanted to use. The total mass of the system m is just this denominator, m1 plus m2 and so on up through plus m sub n. I'll just write it in sigma notation. The total mass of the system m, we refer to m as the sum of the individual n masses. And another term, the moment of the system about the origin is capital M. That's equal to the sum of the individual moments. So in sigma notation, this is from I equals 1 to n, and the terms m sub I times x sub I. Okay, something that might be helpful later on is to observe that this is referred to as the moment of the system about the origin. So each one of those positions, x sub I, indicates how far the point is from the origin, how far it is from x equals 0. Okay, let's do an example. On the x-axis are 3 particles with masses 12, 15, and 20 at locations -3, 2, and 8, respectively. Find the moment, capital M, of the system about the origin. So that just means add the individual moments. Okay, the first particle with mass 12 is located at -3. So the mass 12 times -3. Then we add that to the next moment. The next moment the particle has a mass of 15 and it's located at x equals 2. So this is plus 15 times 2. And then the third particle has mass 20 located at 8. So it's 20 times 8. And let's see, 160 plus 30 is 190, minus 36 is 154. So the moment capital M of the system about the origin is 154. And we also want to find the center of mass. Okay, but the total mass of the system M, we need to have that in order to find the center of mass. The total mass of the system is the sum of the masses, 12 plus 15 plus 20, which is 47. Okay, so X bar, the center of mass, by definition, it's the moment capital M of the system about the origin divided by the total mass of the system. So we get 154 divided by 47. Okay, so this number is a little bit bigger than 3. So it's on that number line, it's to the right of 2 and to the left of 8. So where the center of mass is. Okay, we'll go up to the next dimension. Now suppose there are n particles with masses m1, m2, and so on up through mn, and those are located at n points in the xy plane. So the first point, x1, y1, that's the ordered pair of that point in the xy plane, and so on. And the last point is xn, yn. Analogous to the one-dimensional case are the following definitions. The moment of the system about the y-axis is denoted capital M sub y, because it's about the y-axis. And it's the sum of the moments involving the x-coordinates, so m1 times x1 plus m2 times x2 and so on up through m sub n times x sub n. And then in sigma notation, we can write it this way. Okay, this one is analogous to the moment of the system about the origin. So a few minutes ago, we observed that if we're just on the x-axis, the origin is x equals 0. And the x values were how far the points were from 0 on the x-axis. Okay, well, if we have points in the xy plane, then the distance a point is from the y-axis is the x-coordinate of that point in the xy plane. And another thing that might help, remember the equation for the y-axis? X equals 0. So if it's just the x-axis, x equals 0 is a point. But if it's the xy plane, x equals 0 refers to the y-axis. It's the vertical line on which every x-coordinate is 0. So that if there's any confusion, well, why are we using the x-coordinates if it's the moment of the system about the y-axis? Well, it's because the x-coordinates tell us the horizontal distance a point is from the y-axis. Okay, and the moment of the system about the x-axis. This is denoted capital M sub x, and it's equal to m1 y1 plus m2 y2, and so on up through plus mn yn. Okay, it's the moment of the system about the x-axis because the y-coordinates tell us how far a point is from the x-axis. And the total mass of the system is pretty easy to understand. We just add up the masses, m1 plus m2 and so on, up through plus mn. Okay, so in the xy plane, if we have these n points associated with those n ordered pairs with masses m1 through mn, then there is an ordered pair or a point in the xy plane that is the center of mass, and it's denoted by the ordered pair x bar comma y bar in parentheses. Okay, so what do you suppose the x coordinate x bar is for the center of mass? Just in symbols to start with. So we can use the moment of the system about the origin in the previous example sort of as a guide. The center of mass on the x-axis is the moment of the system about the origin divided by the total mass. So analogously, in the two-dimensional case, the x-coordinate of the center of mass is the moment of the system about the y-axis divided by the total mass of the system. And using the sigma notation, the moment of the system about the y-axis is the sum from I equals 1 to n, and the terms are m sub I times x sub I, and divide by the total mass. So here we're just adding up the n masses from I equals 1 to n. And in the two-dimensional case, the y-coordinate of the center of mass, y bar, this is the moment of the system about the x-axis divided by the total mass of the system. So in the numerator, we have the sum of the moments involving the y-coordinates. And then divided by the sum of the masses. Okay, let's move on to the next page. Here's an example. We have 4 points in the xy plane with their locations and their masses. So in particular, it says find the moments and center of mass of the system of objects that have masses 5, 4, 3, and 6 at the points -4, 2, 0, 5, 3, 2, and 1, -2, respectively. Okay, so we can find the moment of the system about the y-axis, m sub y. So to find the moment of the system about the y-axis, we're going to multiply the individual masses by the corresponding x-coordinates of the point. So the first mass, 5, is associated with the x-coordinate -4, so 5 times -4. Then plus mass 4 times the x-coordinate 0, plus the mass 3 multiplied by the x-coordinate 3, and then plus mass 6 associated with x-coordinate 1. Okay, so we have -20 plus 0 plus 9 plus 6. So what do we get? -5, right? Okay, the moment of the system about the x-axis. So this time we multiply the individual masses by the corresponding y-coordinates. So 5 times 2 plus 4 times 5 plus 3 times 2 plus 6 times -2. Okay, 36. So this time I get 24. Okay, the total mass of the system is just the sum of the masses, 5 plus 4 plus 3 plus 6. So I get 18. Okay, so what is the x-coordinate of the center of mass? So why don't you type that in? What's the x-coordinate of the center of mass? Anybody in here know? Divided by 18? Yeah, -5 divided by 18. So that's the moment of the system about the y-axis divided by the total mass is the x-coordinate of the center of mass. The y-coordinate of the center of mass is the moment of the system about the x-axis divided by the mass. So 24 divided by 18, or 4/3. So let's go ahead and we'll try to graph or plot those points in the xy plane. So one of the points, -4, 2, -4, 2, 0, 5, 3, 2, 1, -2. They have different masses, but the center of mass, -5/18 is a little bit less than -1/3, and 4/3 is 1 1/3. So here is the center of mass, X bar, Y bar. So it seems reasonable that the center of mass would be enclosed by those 4 positions, those 4 points. Okay, now we'll go on to the next level. We'll now consider flat 2-dimensional regions with uniform density rho. And the center of mass of the flat region is called the centroid. If the flat region is symmetric with respect to a line, then the centroid is on that line of symmetry. So if a particular flat region has more than one line of symmetry, then we'll be able to find the exact position of the centroid. So this little exercise is pretty simple. Identify the location of the centroid of a square, a rectangle, an equilateral triangle, an isosceles triangle, and a cardioid. So if we have a square of uniform distance or a uniform density, and a rectangle, an equilateral triangle, an isosceles triangle, and a cardioid. Might look something like this. Okay, well, where do you think the center of mass is on a square? Yeah, right in the middle. There's more than one line of symmetry. One line of symmetry is just a diagonal. So the left right triangle is symmetric with the right triangle. But there's another line of symmetry if you construct a horizontal line through the midpoint of opposite sides. That's also a line of symmetry. And if you have more than one line of symmetry, then the intersection has to be the centroid. So that seems pretty obvious. So that's the centroid of a square. It's right in the middle. A rectangle is not much different. So I'll use a horizontal line of symmetry and a vertical line of symmetry. So the intersection is the centroid. Okay, what about an equilateral triangle where all 3 sides have the same length? How would you describe a line of symmetry for an equilateral triangle? If you bisect one of the sides into two equal line segments, and then construct a line from the opposite vertex, a line segment that attaches that, these are supposed to be right angles. So the two triangles are similar, so that's a line of symmetry. But you can do that with each of the other vertexes and their opposite sides. And each one of those line segments will intersect at a single point, which is the centroid. Hey, an isosceles triangle is a triangle in which at least two of the sides have the same length. So if we have two sides that are the same length, but the third side has a different length, then what about the centroid of that isosceles triangle? How many lines of symmetry does this isosceles triangle have? It has just one. Yeah, so there's just one line of symmetry. So the best we can say is that the centroid is on that line of symmetry somewhere, closer to the bottom base than it is to the opposite vertex. So the centroid is on the line of symmetry. And where it is depends upon the relationship of the length of the two congruent sides and the third side. Similarly, with a cardioid, so a cardioid sort of looks like this. It's supposed to be symmetric. This is supposed to be a line of symmetry. So the centroid lies somewhere on that line of symmetry. Okay, well, some flat spaces or flat regions don't have lines of symmetry at all. So we're going to figure out how to find the centroid of such a region. So let R be the region with uniform density rho in the xy plane between the graph of y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. Explain how to locate the centroid. Okay, so we will use some other paper to do this. All right, suppose we have the graph of some function y equals f of x. So we're assuming f of x is greater than 0 or positive for all x values. So here's our x-axis. And the region will be between x equals a and x equals b. So as usual, since we want to find the centroid of this entire region, we're going to subdivide the interval from A to B into n subintervals, each of length delta x. So the delta x is b minus a divided by n. And we'll focus on just one of the subintervals. From from x sub I minus 1 to x sub I. And we're going to construct a rectangle. The height of the rectangle will be determined by the midpoint of this interval. The midpoint of the interval from x sub I minus 1 to x sub I will be denoted by x sub I bar. And over here, I'll just make a note that x sub I bar, since it's the midpoint or the average of the endpoints, it's x sub I minus 1 plus x sub I divided by 2. And the height of this rectangle will be determined by x sub I bar. Okay, so this ordered pair it's on the graph, and it's also the in the middle of the rectangle on the top of the rectangle. The coordinates are x sub I bar and f of x sub I bar. Okay, so where's the centroid of that rectangle? What are the x and y coordinates of the centroid of that rectangle? Well, we know it's right in the middle. What's the x coordinate of the centroid? X sub I bar. And what's the y coordinate? I know my graph is a little off kilter, but so halfway between the x-axis and the y-coordinate, f of x sub I bar, is 1/2 f of x sub I bar, right? Okay, the distance this centroid is from the y-axis is x sub I bar. And the distance that this centroid is from the x-axis is 1/2 f of x sub I bar. So let's write down the moment about the y-axis for the ith rectangle. What is that? let's see, a moment is mass times a distance, right? So what's the mass of the rectangle? We're assuming that it has uniform density rho, and so the mass of a rectangle is the density times the area. So rho times whatever the area of that rectangle is the mass. So we're going to multiply the mass. It's rho times the area of the rectangle. Well, the height of the rectangle is f of x sub I bar, and the width is delta x, right? So rho times f of x sub I bar times delta x. This is the mass of the rectangle. I'll just refer to this as rectangle r sub I, mass of r sub I. And then we multiply this by the distance that the centroid is from the y-axis, which is x sub I bar. So this is distance from centroid to the y-axis. So if you're wondering about that, remember when n is extremely large, these rectangles are extremely thin. So it's almost like saying, how far is it from the rectangle to the y-axis? So for a really thin rectangle, well, the distance is about x sub I bar, right? Okay, so if we rearrange this, we can write it as rho times f of x sub I bar times x sub I bar times delta x. Or you could put x sub I bar times f of x sub I bar also. Okay, well, if we do that for all n rectangles, then the moment of the region about the y-axis is approximately equal to the Riemann sum from I equals 1 to n of rho times, I'm going to write it as x sub I bar times f of x sub I bar times delta x. And then if you take a limit of this Riemann sum by letting n go to infinity, then the moment of the entire region about the y-axis is the definite integral from a to b of rho times x times f of x dx. Okay, what about the moment of the rectangle about the x-axis? Well, each of the terms is a mass and then multiplied by the distance that the centroid is from the x-axis. So we're running out of time. So the mass is the same as it was in the previous for the moment of the system about the y-axis. So it's rho times f of x sub I bar delta x. This is the mass. And then the distance that the centroid is from the x-axis is 1/2 times f of x sub I bar. And so if we rearrange this, we get rho times 1/2 times the square of f of x sub I bar, delta x. We do that for each of the n rectangles and then take the limit. We get the moment about the x-axis equal to the definite integral from a to b of rho times 1/2 times f of x squared dx. Okay, we're out of time. We'll pick it up from here tomorrow and finish section 8.3 tomorrow. Go ahead and sign in for attendance.